Hello, everyone. Hope you all are well. Today, we're going to be talking about ethers and oxymercuration. So, some small housekeeping things that you should know. I want you guys to pause the video. If this is your second, third, fourth time watching it, if you're doing review, right? I want you guys to pause the video and attempt to do these problems over and over again. This is a universal rule just for studying this class in general as well. I want you guys to either have some sort of practice scheme, right, that forces you to remember different types of reactions and different types of mechanisms. Ideally, I recommend using flashcards. Anki is a really good one. It's a free flashcard source. If you guys want help with kind of figuring out how Anki works, come find me. I'll probably help you out with that. And essentially, right, what you have to do is I recommend that if, for example, if Dr. Ko writes that, okay, reaction, if you have reactants A and then reactants B, that equals product C. And this whole thing is called reaction, whatever, so and so, yada, 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 right? And so what I want you to do is that I want you to blot out certain parts of the reaction, right? And so now, right, in the flashcard, you have to figure out, okay, what do I have to add to A to get to C? Or if I have A plus B, right, what does that make me, right? And that should be able, if you do that over and over and over again, you should be able to quickly and rapidly familiarize yourself with the course content. And so there's two things I also want you to keep in mind as well, right? I want you guys to prioritize predict the product. Mechanisms can be scary if you suck at them, right? I wouldn't worry about it that much. Yes, practice them, but I want you to prioritize being able to predict the product. That's what PTP stands for. I'm just gonna predict the product. Do that. Yep, predict the product. That. And so, that's the main priority because you're going to get most of your points from there. Mechanisms, right? You can do that. You can do that later, honestly. But I want you guys to prioritize this first before you attempt the mechanisms because how are you going to do the mechanism if you don't know what the end product is, right? So that's just a couple things you want to keep in mind. So without further ado, let's jump into ethers, right? First and foremost, right? What is an ether? An ether is any type of structure where you have a oxygen, right? That's surrounded by a bunch of other carbons. You can also have like, um, ethers that are like this, right? Ethers that are like this. You can have this. That's an ether too. Some of these ethers have names, but I mean, I don't. Naming's not really in my wheelhouse. But the main point here, right, is that you were able to identify that all of these structures that I just drew are ethers. And so one of the things that that ethers are characteristic of is that the carbons, right, that are right next to the ethers, right, their CH bonds are really, really weak. And so these H's right here, these H's right here, right? H's right here, these right here. And what's going to happen is that these CH bonds are going to be really weak and it's going to enable a reaction. So the reason why they're weak, right, is because presence of oxygen enables CH bonds to be weak. And then the implication is that I have a reaction. Reaction time. So the one ether reaction we're going to have to wrap your head around, right, is that when you have ethers and what happens if they're exposed, I'm going to move this over here. What happens if they are exposed to oxygen, to O2? So this is a very important part right here. Okay, right? So with this, right, you're going to form two products, right? And we're going to get to those in 1 second, right? But first and foremost, right, before we talk about the two products that you form from this reaction, right, of ethers and O2, there first has to be a preparation step. I like to call it a preparation step. I don't know if that's a common chemistry thing, but it's basically what it is, right? So the first preparation step that you go through, right, is that you get your little O2 here, right? And you guys should be familiar with this, right? This is just O2 written out. What's going to happen is that this little O2 right here, right? If you notice that wait a second, there's a dot right here, right? That indicates that it's a radical, right? It's just a singular electron. I know it looks a little weird because I'm sure you're used to like when you do reactions, right? It's two electrons in a pair going after and doing chemistry stuff, but in this case it's just one. So yeah, here's an H right there. I should probably make the H a little longer. Give me 1 second. There you go. It's a long AFH. But the first step, right, is that this O2 is going to steal an H. So what's going to happen is that this is going to happen, and this is going to pop onto here, and this pops off into here. Now, what I just did here, right, is I drew three arrows. The first arrow, right, is that this is going to go, this radical is going to go over here and initiate. One of the electrons is going to come over here and meet them in the middle to kind of form a bridge and eventually form a bond. And then from here, right, since we're only reacting, right, with one electron, the arrows are going to be half, right, which I'm sure you guys are probably deduced by now. And the other half of the electron is going to go back onto this carbon right here. And so the result is that you get a reaction as so. You get some products like this. You get your original ether right there, right? But now you have this little dot right here to indicate that the only thing that's left, right, is that singular radical. And then you have O2 that is like this. Yep. And this guy's still hydrogen. It's like that. Okay. So these are the two products that occurred from this. And then the second step of this, right, is that this little guy right here is going to go. It's going to find another O2, right? It's going to hook itself onto another O2. And this time, right, since there's already two radical points right here, right, ready to react with each other, they can just quickly just kind of go and do their thing. Yep. And thus you end up with this right here. Yep. So this is the end of the preparation phase. I'm gonna go ahead and scoot myself up here because I'm the king of running out of space. It's actually incredible. I should make an Olympic sport out of it. I get gold medals every single time. So from here, there's two directions by which you can go, right? And so the first direction is going to be the fastest, the fast direction, right? So very rapidly, once you form this kind of product right here, right? Once you form this product, what's going to happen is that you could see your little product over here, finding an H from another one of your starting materials. And now remember, if you're wondering, wait, where the heck did you get this little starting material from? Remember that when you throw certain reactants into a mixture with each other, right? There's not just one. This is one instance in like hundreds of thousands, right? Or even millions, right? Of your starting material bouncing around into your solution. And so if I had another one of these, right? Actually, no, I'm making another color. I'll make this orange, right? So you're going to do a very, very similar reaction to your first step, to your first preparation phase, right? This guy's going to go into here. It's going to go into here. This pops off onto here. And then eventually, right, you're going to end up with this product right here. This is the result of this is the reaction that usually happens very, very quickly. And this product is called hydroperoxide. Probably have heard of it. Hydroperoxide. So this is fast, right? This whole thing is fast. Now, if you let this reaction kind of just the solution kind of just sit there for months, you're going to end up with a definitely other product. You're going to end up with another product. This is the slow part, right? We're talking about months here. What's going to happen is that this one's relatively simpler, I would say, right? You can get this. I'm going to change this to red. Sorry about that. Forgot I'm going to color code things, right? So when you have the slow direction, right? It can find another one of your reactants from the first preparation phase. You'll form onto this, and then you'll form this. Actually, no, that's probably not correct. There you go. Yep. This is just called peroxide. Yep. And so this is the two directions you can go, right? Remember, first we have a preparation phase, right, where you kind of enable all the radical stuff nonsense to happen. And then from there, once you hit this step right here, you can go the fast route, right? Which generally happens really, really quickly. Then you can go the slow route, right? Which if you let the solution there over months, it'll form this. Some fun facts, right? Apparently this detonates without warning. So if you're ever working with this in a lab, be very careful. Also, don't bring that on a plane. It'd be a really good time for you or federal air authorities, I guess. So just be careful with this. But anyways, so this is basically all of the ether reactions we're going to really deal with in this class. And so if you have any other questions, right, please let me know and pause this video as well. Alrighty, cool. Whew, first reaction done, out of the way. From here, we're going to go to oxymercuration, which is sorry, this is not the full name. Oxymercuration, demercuration. This is a mouthful. So sometimes you'll probably hear me call this oxymerc for short. This is not actual formally recognized convention, so don't worry about it. Anyways, so the thing that you're going to form with this, right, is that I can confidently draw this from here. So you're going to form a you're going to you start with a double bond, and you're going to end up with an OH. Yep, you're going to end up with an OH here. And so I want you guys to kind of sit and kind of really, really take this in. So we're gonna go by this very slow. Oxymerc, right? This reaction right here. You take a double bond, right? And by the addition of I don't know what these are actually called, right? Mercury something, right? HGOAC2, H2O. And then after that, once after you add NaBH4 and NaOH, right? You're going to get an OH on the most substituted side of the alkene. Okay? Yeah. So this is the part where I said like please prioritize PTP. If I gave you, right, just the products. No, no, sorry, just the starting material, right, and the reactants, you should be able to accurately predict, okay, this is going to be the product. Or if I just gave you, the starting material and the product, you should be able to figure out the reactants. Yeah? And so please, please, please make sure of that. Now, so the reason why oxymercuration is a thing, right? It made me asking yourself, right? Why don't we just like, I don't know, throw this in with HCl, H2O, right? Why don't we want to just use this reaction from 8A to quickly kind of do the reaction? Well, what's going to happen, right, is that the reason why we don't do this, the reason why might want to do oxymerc is because that if you did this reaction right here, going down this route, right? Um, if you took that alkene and you eventually threw it in with there, what's going to happen is that, well, you're going to end up with a scenario like this, right? The H is going to be here, right? The H reaction is going to be here, and then you're going to have a plus charge right here, right? And now normally, right, you think to yourself, okay, right, from here we just take OH and just, go in and react right there, right? But unfortunately, what's going to happen is that you're going to have something called a carbocation rearrangement, right? And so what I mean by that, right, is that the carbocation rearrangement is that you're going to take one of these, CH3s, move it over here, right? And then you're going to do a carbocation rearrangement. You're going to end up with, let's see, make sure I got this correct. You're going to end up with this. It's a rearranged product, right? You're going to end up with this. And then from here, the OH is going to be right here. Oops, I forgot to draw that. OH is going to be right there. And so if you want this product right here, right? If you want the OH to, for sure, without a doubt, without any of the CCR nonsense going on, if you want it to be right here, right? Then you probably want to consider oxymerc. Um, so yeah. With that being said, right? I'll just write this in red, right? Oxymerc avoids carbocation rearrangement. Good times. Alrighty, cool. So, like you said, right? I'm gonna go ahead. I'm gonna redraw this problem over here. Actually, you know what? I should just copy and paste it. What am I doing? Alrighty, cool. So let's walk through this reaction step by step. So first step down here, right, is that we're going to obviously react with the first set of reactants we have here. And so we're going to have ACO, HG, right? This OAC right here, right? This is just this written out. Yeah. And so what's going to happen, right, is that you're going to get this double bond going to go into your reaction. It's going to hit this mercury here, this Hg. This is going to bounce off in response. And so this is a very, very common motif of a lot of reactions. If you're very, very confused, right, just know that you go from electron dense to electron poor, right? Because mercury is very electron poor because it has, well, it has oxygens that are kind of pulling the electrons towards it, right? And then in response, something else bounces off. Yeah, I would liken it to like if a meteor fell and like fell onto your street, it would cause people to run away, right? So meteor, right? Whoops, it's not meteor, people running away. Hmm. So from here, you are going to get a product like this. You're going to get this. Let me just make sure to draw this very carefully. Alrighty. You may be wondering what I just drew here, right? So this is just this. Yeah, I just flipped it around a little bit. Hmm. Now you may be wondering, what the heck is all these dotted lines, right? What are these symbols, right? So when you guys get to the step of the reaction, right? There's going to be some st charge stabilization, right? So this HD over here, right, is having I won't say the best day, right? It has a charge on it, right? But however, right, this charge is stabilized by the other reaction site over here, right? So there's going to be a charge stabilization interaction happening here, right? So charge stabilization happens here, right? And then when that happens, right, it's going to attract an OH, right? The next step is going to have H2O come in here. Going to go into here, and then it's going to pop off this way, and then you are going to end up with this. I kind of liken this to like a doorway swinging open, you know? Let me color code this. This is gonna be blue. Mhm. This is going to be blue. Sorry, hold on. Let me just, it's not just an OH just yet. Give me 1 second. Hmm? And that should be it for this part, right? And so I want you guys to take a notice at this, right? So this H2O comes in here and attacks. And once it attaches itself onto here, right, there is a plus charge onto it. Now, why does that plus charge exist? So that plus charge exists, right, because this oxygen right here, right, has right now in this present moment too many bonds on it, right? Way too many bonds. And so this is going to be also something that's very, very important in the coming weeks and months ahead, because you need to be able to clean up your charges really quickly. Oxygen doesn't want to be in this charged state for a really, really long time. So what's going to happen, right, is that you're going to have to do a quick proton transfer. Proton transfer. You can use any base, honestly. Usually what's floating around is like one of the OACs, right? This OAC is from this guy over here, right? So I can just highlight this in orange. Yeah. So this came from another step above. Remember, they're all floating in the same solution together. So you can literally just pull whatever you want to use as a base if it makes sense. This is going to pop off onto here. This is going to grab that H. This is going to pop off right here. And then you're going to end up with this. Right? This OH is going to be there, all cleaned up. Sitting tidy and pretty. Just chilling there. Yep. And so the last step is what the heck do we do with this HGOAC, right? If you stop the reaction right here and said, all right, I'm done, that would be incorrect, right? Because we established up here, right, that the predict the product, you get this, right? Yeah, I don't see any HGOAC hanging off on the side. So it's going to require another step, right? This is where the NABH4 comes in, right? Now you're going to go way more into depth with this later, right? But NABH4, right, is going to generate hydrides. Now this is going to seem super weird to you, but it'll all make sense later, right? It's NABH4, right? Plus, what was it? NaOH. It's going to make hydrides. Maybe asking yourself, what the heck is this? What is this? Honestly, the best I can describe it, right, is that H is in certain configurations, right, you can turn a hydrogen into something that's really nucleophilic and go to attack. This is called a hydride, right? Um, it's like a hydra, right? It's like H turning into a hydra, like the mythical monster. And it'll go, it'll attack here. This will pop off. And then from there, right, you'll finally get your product. If you're confused about the hydride stuff, don't worry about it. We're gonna talk more about that later. Just just trust me on this one. Just trust me, bro, you know? I'm gonna go ahead, I'm going to highlight this. This is gonna be purple. Why not? Yep. Then we have purple right here. And so, right, if are we done now? Well, let's take the product that we got right here, right? Let us scroll all the way up over here, right? And well, yeah, it looks like it, right? This is your product. So that was oxymercuration, demercuration, and the one ether reaction you have to wrap your head around. Um, I'm not really too keen on names per se. I prefer you guys kind of understand how it works. So I hope you guys have an awesome day and good luck studying. See you around.